We have seen the definition of divisibility. We know what is meant by saying that a number A divides number B. We have seen a few properties also regarding divisibility. Now we are going to discuss something related to common divisors. Suppose A and B are two given integers, then obviously the term common divisor means that a number C such that C divides A and C divides B. That is, C is in the set of all divisors of A as well as set of all divisors of B. So we can probably think about the greatest common divisor of A and B. But there is one question remaining. How can we make sure that such a greatest element exists in that set of all common divisors? For example, suppose that the set of all common divisors is something like the set of all natural numbers, and in that case, there is no largest natural number, and so we cannot find the greatest common divisor. So we have to be little bit careful while trying to define the greatest common divisor. To discuss the concept of greatest common divisor, we will quickly recall the concepts like divisor, common divisor, etc. For given integers a and b, we defined a divides b, or we set a divides b if there exists some integer q such that b equal to a q. So this is concept 1. What is meant by saying that an integer a divides b? Concept 2. If c belongs to z, that is c is an integer, is such that c divides a, where a is given, and c divides b, then c is said to be a common divisor of a and b. For example, suppose that we consider a to be equal to 35 and b to be equal to 56. Then what are the divisors of a? Suppose that we name the divisors of a by divisors of a. Suppose that we call that set, this is set because divisors of a there can be many, and so we will put them inside a set and denote that set by dA. So divisors of a are, we know that 1 divides 35, after that 5 divides 35, then 7, and after that 35 itself. These are divisors of a. Similarly, divisors of b are dB. So these sets are, these elements are 56. So 1, 2, after that 4 is there, 7 is there, 8, 14, 28, 56. These are the divisors of B. So common divisors of A and B. Suppose that we call this set, we denote this set like this, then this is going to be equal to, so we have to take the intersection of A and B. So this is dA intersection dB, and this is nothing but equal to 1 is common, and after that 7 is common, and that's it, 1, 7. Okay, so we have formed the set of four common divisors of A and B, and that set consists of just two elements. Now, greatest common divisor. So from the very phrase itself, it's very clear that we are talking about some integer that commonly divides A and B. If you want to call that integer as the greatest common divisor of A and B, it must be an integer, it must be a divisor of A, it must be a divisor of B, and it must be the greatest among all the common divisors. So the definition is, or the expansion of this means, if let A be integers, D is the greatest common divisor, or in short, GCD, if there are two conditions. D is a common divisor of A and B, and the second condition is D is the largest among common divisors of A and B. So there are two conditions. Condition one is that D is a common divisor of A and B. That means that D must be a divisor of A, and D must be a divisor of B also. Not only that, if you have, there may be many divisors of A and B. That means there can be many common divisors of A and B. In that case, D must be the largest among these common divisors. If D satisfies these two conditions, we say that D is the GCD of A and B, and we write D equal to GCD AB. And sometimes we will simply skip this word GCD and we will simply write in ordinary bracket like this. So this should not be confused with the ordered pair notation, or the notation of intervals in the real line, because we will not be dealing with in the intervals most of the time. So we don't have to worry about that. Most of the time we will be using the symbol in ordinary bracket AB to denote the GCD of A and B. We will see a few examples. We have already seen that A is equal to 35, B is equal to 56, 35, 56. Then common divisors, we found to be 1, 7. And what is the largest in this? This is the largest. So GCD of 35, 56 is 7. So another example, A equal to 24, B equal to 24 itself. So what are the common divisors? Since A and B are the same here, we don't have to take any intersection or anything like that, because we have just one set. We need to only consider all divisors of A. So divisors of A, suppose we denote it by dA. This is 1, 2, 4, 6, 8, 12, and 24. So what is the largest? DB is the same as DA, because A is equal to B. Therefore, the intersection is going to be equal to just DA, and 24 is the largest. So GCD of 24, 24 is equal to 24 itself. So in some other word, in some other sense, we know that given a number, that number itself is always a divisor of that number, and the largest divisor of number cannot exceed that number itself. Therefore, if we are asking the GCD of a number and the same number, then it's always going to be that number itself. So that is a very quick observation. So the observation is the following: the GCD of AA. Of course, we haven't proved it. We are just looking at this example. We are making a guess. What is the guess? GCD of A is equal to A itself. So we have to verify this. Now another example. Suppose that A is equal to 12, B is equal to 24. Then divisors of A is going to be 1, 2, 3, 4, 6 and 12, and divisors of B is going to be equal to 1, 2, 3, 4, 6, 12 and 24. So the intersection common divisors of A and B is 1, 2, 3, 4, 6 and 12, and the largest is this. This is the GCD. So here what we are observing is A actually divides B. So common divisor means that it has to divide A and B. What is the largest divisor of A? Largest divisor of A is A itself. And A now divides B. So largest divisor, another quick observation from this particular example is that GCD of two numbers cannot exceed any of them, or GCD is less than or equal to minimum of these given two numbers. That's an observation, but we are yet to again prove it. So another guess. GCD of A and B is less than or equal to A GCD, because it has to divide A. GCD of A and B is less than or equal to B. Therefore, since it is less than or equal to both this A and B, GCD of AB is going to be less than or equal to minimum of AB. Therefore, here we have A equal to 12 and 12 divides 24, and GCD cannot exceed 12. Therefore, the largest divisor is going to be automatically equal to 12. So the observation here is that if one number is a divisor of the other, so we have another guess. If A divides B, one number is a divisor of the other, then GCD of AB equal to A. So we will try to verify all these things using the techniques that we already know. Rigorously, we will try to verify, not using examples. But before that, we will go to something else. We have defined the greatest common divisor of A and B in the following way. An integer D is said to be the greatest common divisor of A and B, provided D is a common divisor of A and B, and after that, D is the largest among all divisors of A and B. That means common divisors of A and B. Now, a symbolic definition can be much more useful, because we will be most of the times dealing with problems involving symbols. So we are going to define the GCD using some symbols. The symbolic definition of GCD that we are going to propose is the following. Let A, B be positive integers. D belongs to n, or D, another positive integer, is the GCD of A and B if the following two conditions are satisfied. If D satisfies the following conditions. So what are the conditions? Condition number one. D is a common divisor of A and B. That means D divides A and D divides B. So just we are going to say that D divides A and D divides B. What is the second condition? D must be the largest among common divisors. Therefore, if C is a common divisor, D is the largest. Therefore, C is a common divisor. What should be the relation between C and D? D is the largest. Then C must be less than or equal to D. These are the two conditions that D should satisfy, so that we can call D as the GCD of A and B. Now, there are a few questions remaining. why we are defining GCD of positive integers alone? Why can't we define the GCD of negative integers and 0? That is one question remaining. So how did we define GCD? We define GCD to be the set of consider the set of all common divisors and then take the largest. So we know that if a number has a negative divisor, the modulus of that divisor is also going to be a divisor of that number. For example, so observation 1. If C divides A, then minus C also divides A. Why is that? Suppose C divides A, then there exists Q integer such that A is equal to CQ. But then we can write that so how do we bring this minus C here? A is equal to minus C into minus Q. Since Q belongs to Z, this minus Q also belongs to Z. Therefore, minus C divides A. Therefore, whenever we have a divisor of that number, a particular number, negative of that also divides that number. Therefore, even if we consider negative divisors, still there will be positive divisors also for that particular number. We are talking about largest common divisor, or we are talking about largest divisors. So a number definitely must be having positive divisors, and therefore the largest is always going to be a positive integer, because whenever there are negative integers and positive integers as divisors of two numbers, the largest is always going to be positive ones. And we know one more thing, that whatever negative number is there as divisor of A and divisor of B, we know that 1 is a divisor of A and 1 is a divisor of B. Therefore, 1 is a common divisor of A and B. And since we are looking for the largest common divisor, no negative integer can be the largest common divisor of A and B. So the next observation is this: no negative integer can be the GCD of A and B. Why is this? Because every negative integer is going to be less than 1, and 1 is the common divisor. So largest common divisor must be greater than or equal to every common divisor. Therefore, largest common divisor must be greater than or equal to 1. The reason is this: since 1 divides A and 1 divides B, largest or GCD of AB must be greater than or equal to 1, and so it is always positive. So the condition we have taken here, that D belongs to N, is not really necessary. So D cannot be actually, D is if D satisfies these two conditions, that D divides A and D divides B, and if C is some other divisor, then C less than or equal to D, the second condition automatically makes D to be positive. Therefore, saying that D divides N is not actually necessary. D is an integer is more than enough. Now, why we are taking A and B to be positive integers? Can't we find the GCD of negative integers also? So that can be answered from the following observation. So the observation is the following, and we can probably start with an example. Suppose that we have A equal to minus 24 and B is equal to 24, or B equal to 32. So we have A negative integer, B a positive integer. Recall that what we said in the previous step, that we are considering only positive integers, only positive divisors, because we want to find, see, of course, whenever we are talking about divisors, we can think about positive as well as negative divisor. But since we want to find out the largest among the divisors, since if one number divides A, then its negative also divides A. So if at all we are taking some negative divisor, there is a corresponding positive divisor. So we will strictly keep ourselves within the set of all positive divisors. So CA we can consider to be the set of all positive divisors of minus 24. But set of all positive divisors of minus 24 is going to be the set of all positive divisors of. So this is the observation equal to C24. That's equal to again 1, 2, 3, 4, 6, 8, 12, 24, and C32, that is CB, equal to 1, 2, 4, 8, but next it's 18, sorry, 16, and 32. So now if we take the common divisor, see the process we finally brought down to considering modulus of A instead of A. Therefore, if you want to find the GCD of A and B, it is equivalent to find the GCD of modulus of A and modulus of B. So this is the observation. GCD of AB is equal to GCD of modulus of A, modulus of B. So we don't have to worry about the sign of A and B, or we can always assume that we are going to find the GCD of modulus of A and modulus of B. That's why we wanted to insist here that we wanted to especially mention here that A and B are positive integers, because if we define GCD for positive integers, automatically we are going to define it for negative integers also. But there is in fact a mischievous case remaining without being noticed. The case is the following. So the question is, uh, can we find, see, positive is all right, negative is all right, but there is somebody standing in between, that's 0. Can we find GCD of 0 and B where B not equal to 0? So definitely, because what are the divisors of 0? What are the numbers going to divide 0? C0. So one definitely, positive divisors only we are considering. One definitely divides 0, because we know that 0 is equal to 1 into 0. So 1 divides 0, 2 divides 0, because 0 is equal to 2 into 0, 3, etc. Therefore, this is going to be equal to the set of all natural numbers itself. And what is CB? This is some set. We don't know what exactly it is. It is non-zero. Therefore, it's not going to be equal to the set of all natural numbers. And this is actually a subset of n, because we are considering the divisors, positive divisors of B. Therefore, this is subset of n. So what is the intersection of these two? We know that if you have a set A and a set B, set A, B, such that A subset of B, or here it's the other way, B subset of A, then A intersection B, that means common divisors, A intersection B is going to be equal to B itself. Therefore, we have these two sets, and the intersection is going to be just equal to C0 intersection CB. So C0 intersection CB is going to be equal to CB itself, and therefore GCD of CB is nothing but largest in CB, that is largest divisor of B itself. Therefore, whenever 0 is involved and the other number is non-zero, we don't have to worry about finding the GCD, and that is going to be just the largest divisor of. But what is the largest divisor of B? We have taken B to be a non-zero integer, and therefore what is the largest divisor? Largest divisor of B is going to be equal to modulus of B. So GCD of 0B here, not CB. GCD of 0B is going to be equal to modulus of B if B is non-zero. Now there is another question. What is GCD of 0 and 0? So A and B both 0. Now the problem here is this. So if you consider the set of all positive divisors of 0, that is equal to the set of all natural numbers, and this is equal to, this is A, this is B, therefore CA is this, CB is also this. So the intersection is going to be equal to N. CA intersection CB is N, and N has no largest element. So we cannot find the GCD of 0 and 0. So there is no question of finding GCD of 0 and 0, and cannot be found. So whenever we are trying to find the GCD of A and B, we will assume that, so the assumption is the following. Whenever we talk about GCD, talk about GCD of A and B only when A and B are not simultaneously 0. That means AB, AB are not 0 together. This is a crucial condition and very important condition. We will talk about GCD of A and B only when A and B are not 0 together. That means one of them must be non-zero. That is, one of them must be non-zero. If you want to talk about GCD of A and B, one of them must be definitely non-zero. So this condition we have to keep in our mind.